When you have more than 3 current-carrying conductors in a raceway or cable, you must derate the ampacity of the conductors. This is to prevent overheating due to the combined heat generated by the conductors. National Electrical Code Table 310.16 provides ampacity values for conductors based on their insulation type and temperature rating. To determine the correct ampacity for a conductor, you need to know its insulation type. If you are working with stripped non-metallic sheet cable, often referred to as NM cable, and you do not know the specific insulation type of the individual conductors within the cable, you must use the 60°C column in Table 310.16. NM cable, by default, is rated for 90°C, but the 2020 NEC Section 334.80 states that the 90°C rating shall be permitted to be used for ampacity adjustment and correction calculations. The ampacity shall be so adjusted that the allowable ampacities for application do not exceed those determined by the 60°C column of Table 310.16. This means that for practical application, the ampacity is limited to that of a 60°C rated conductor. Therefore, when selecting the appropriate ampacity from Table 310.16 for stripped NM cable with unknown insulation, refer to the 60°C column. For example, if you have a 14 American wire gauge copper conductor, the 60°C column would indicate an ampacity of 15 amps. If you have a 12 American wire gauge copper conductor, the 60°C column would indicate an ampacity of 20 amps. If you have a 10 American wire gauge copper conductor, the 60°C column would indicate an ampacity of 30 amps. Once you have determined the initial ampacity from the 60°C column, you must then apply any necessary derating factors for the number of current-carrying conductors in the raceway or cable. National Electrical Code Table 310.15 provides adjustment factors for more than 3 current-carrying conductors in a raceway or cable. For example, if you have 4 to 6 current-carrying conductors, you must derate the ampacity to 80% of its original value. If you have 7 to 9 current-carrying conductors, you must derate the ampacity to 70% of its original value. If you have 10 to 20 current-carrying conductors, you must derate the ampacity to 50% of its original value. If you have 21 to 30 current-carrying conductors, you must derate the ampacity to 45% of its original value. If you have 31 to 40 current-carrying conductors, you must derate the ampacity to 40% of its original value. And if you have 41 to more than 40 current-carrying conductors, you must derate the ampacity to 35% of its original value. It is important to note that these derating factors are cumulative. For instance, if you have conductors exposed to ambient temperatures exceeding 30°C or 86°F, you may need to apply additional correction factors as specified in Table 310.15 bone. Let us consider an example. Suppose you have 6 12 American wire gauge stripped NM cables, each containing 2 current-carrying conductors running in a single conduit. The conductors are copper and the ambient temperature is 35°C. Firstly, determine the baseline ampacity from the 60°C column of Table 310.16 for a 12 American wire gauge copper conductor. The ampacity is 20 amps. Secondly, calculate the total number of current-carrying conductors. 6 cables with 2 current-carrying conductors each gives you 12 current-carrying conductors. Thirdly, determine the derating factor from Table 310.15 for 12 current-carrying conductors. The derating factor is 50%. Fourthly, calculate the derated ampacity. Multiply the original ampacity of 20 amps by the derating factor of 0.50, giving you a derated ampacity of 10 amps. Fifthly, determine the temperature correction factor from Table 310.15 bone. Assuming the conductors have a temperature rating of at least 60°C and the ambient temperature is 35°C, the correction factor is approximately 0.87. Sixthly, apply the temperature correction factor to the derated ampacity. Multiply the derated ampacity of 10 amps by the temperature correction factor of 0.87, giving you a final ampacity of 8.7 amps. Therefore, in this scenario, the 12 American wire gauge conductors can only carry a maximum of 8.7 amps due to the combined effects of the number of current carrying conductors and the ambient temperature. It is crucial to understand and apply these derating and correction factors to ensure the safe and reliable operation of electrical systems. Failure to do so can lead to overheating, insulation damage, and potentially electrical fires. Another important consideration is the type of termination devices used with the conductors. Some termination devices are only rated for 60 degrees Celsius or 75 degrees Celsius. In such cases, the ampacity of the conductor must be selected based on the lowest temperature rating of any connected termination device. This requirement is outlined in NEC section 110.14c. For example, if you are using a circuit breaker that is only rated for 60 degrees Celsius, you must use the 60 degrees Celsius column in table 310.16 to determine the conductor ampacity regardless of the conductor's insulation rating. Let's consider a few additional scenarios to illustrate the application of these rules. Scenario 1. You have 14 American wire gauge THHN conductors in a conduit, supplying power to a lighting circuit. The ambient temperature is 30 degrees Celsius, which is 86 degrees Fahrenheit, and the termination devices are rated for 75 degrees Celsius. Firstly, determine the baseline ampacity from the 75 degrees Celsius column of table 310.16 for a 14 American wire gauge copper conductor. The ampacity is 20 amps. Secondly, determine the derating factor from table 310.15 cone for 4 current carrying conductors. The derating factor is 80%. Thirdly, calculate the derated ampacity. Multiply the original ampacity of 20 amps by the derating factor of 0.80, giving you a derated ampacity of 16 amps. Fourthly, since the ambient temperature is 30 degrees Celsius, no temperature correction is needed. Therefore, the final ampacity for the 14 American wire gauge THHN conductors in this scenario is 16 amps. Scenario 2. You have 10 American wire gauge conductors with XHHW insulation in a conduit, supplying power to several small motors. The ambient temperature is 40 degrees Celsius, which is 104 degrees Fahrenheit, and the termination devices are rated for 75 degrees Celsius. Firstly, determine the baseline ampacity from the 75 degrees Celsius column of table 310.16 for a 10 American wire gauge copper conductor. The ampacity is 35 amps. Secondly, determine the derating factor from table 310.15 cone for 7 current carrying conductors. The derating factor is 70%. Thirdly, calculate the derated ampacity. Multiply the original ampacity of 35 amps by the derating factor of 0.70, giving you a derated ampacity of 24.5 amps. Fourthly, determine the temperature correction factor from table 310.15 burn for XHHW insulation at 40 degrees Celsius. The correction factor is approximately 0.88. Fifthly, apply the temperature correction factor to the derated ampacity. Multiply the derated ampacity of 24.5 amps by the temperature correction factor of 0.88, giving you a final ampacity of 21.56 amps. Therefore, the 10 American wire gauge conductors with XHHW insulation can only carry a maximum of 21.56 amps in this scenario. Remember to always consult the latest edition of the National Electrical Code and any applicable local codes for specific requirements in your area. Electrical codes and standards are regularly updated to reflect new technologies and best practices for electrical safety. In summary, when determining the ampacity of conductors, especially stripped NM cable with unknown insulation, always start with the 60 degrees Celsius column of table 310.16. Apply any necessary derating factors for the number of current carrying conductors, and consider the temperature rating of the termination devices. It is also very important to know that THHN is the answer, because it has a high heat resistance. Proper application of these rules will help ensure the safety and reliability of electrical installations.